All right, ladies and gentlemen, welcome to today's lesson about analyzing histograms. To really be successful at this lesson and this assignment, you'll want to make sure you know how to make a histogram. That's really important because you can't read the graph if you don't know how it's made. Well, making it tells you a whole lot of stuff. And so being able to read them is important for this unit because a lot of data is out there in the world. You got to be able to interpret graphs that look like these. Histograms are fairly common in the wide world out there, the real world. And so what's going on is we got 3 histograms here. And they're showing the batting averages of winners of the batting title in Major League Baseball for different year groups here, right? These are 30-year spans, the early 1900s, the mid-1900s, and then the late 1900s. And these are the batting averages of the winners here. And so we're going to be reading them. A few things to remember about histograms is the height of these bars here are how many people were in each of those categories, like each of those bins. And so if we're looking here, let's kind of zoom in a little bit here. So each of these tick marks here does represent 0.01 of an increase in batting average. So this bar here being 9 tall means there was 9 people who had a batting average between 0.350 and 0.36. So this is 0.36. And so there's that little span there, and there are 9 people. And so there you go. That's kind of a few things to remember. Now we're going to be asked quite a bit of questions about these 3 graphs here. How many batting titles are won with a batting average between 0.3 and 0.35 in the 01 to 1930 category? So we're looking from 0.3 here to 0.35. And now we have to count this up. You're going to figure out how tall these bars are, which is that one's 1 tall, this one's 4 tall, this one's 6 tall, this one's 2 tall. And you're going to add those up. 4 plus 6 is 10, plus 1 is 11, plus 2 is 13. So looking at 13. And then you go to the next one. How many batting titles are won with the batting average between 0.3 and 0.35 in 1931 into 1960, which is this graph. And again, we're looking from 0.3 to 0.35. And you get how tall these are. And you're going to add them up. I'm going to let you do that first. So go ahead and figure out how tall these are, add up those numbers, and that should be how many. Okay, I got the other 1, 7, 4, and 13 tall. If you add those up, you should be getting 25. So I'm going to come over here, 25, 25. And let's see if you can get it all by yourself on question 3. Go ahead and pause and get it. All right. Did you get 40? Because that's what I got. And, this might have a little bit of variation in the answer because we don't have exact grid lines. It's not like halfway between them. And so we got to make some assumptions about how tall these are, but these are my best estimates. This one's 1, this one's 3, 11, 19, and 6. If you add them up, you're looking at 40. If you had slightly different numbers, 1 higher, 1 lower, that's okay. And we'll just kind of go from there. And then we got question 4. If you were to find the mean of each of the winning batting averages for each time period, which time period do you think would have the highest mean? And then explain. All right. So let's look at these graphs here. We got so remember the mean is the average. And typically the average of a histogram is the average of a normal set of data is really close to the median, and that's kind of like the middle of the data. An average is a center. So if you look at your batting averages here, you kind of draw a little shape like that. Our batting average is looking like about here. Maybe down a little bit. This number will drag it down a little bit. But yeah, our batting average is, I'm looking like about here. And if we do the same thing here, our batting average is clearly lower, right? Our batting average is looking like here, maybe pulled right a little bit because we got a little bit of tail over here. And then on this next one, Yeah, we got a longer tail over here, but we're looking at an average. If this was the kind of top peak there, since it has a tail over here, it's going to pull our average to the right a little bit, right? If you have higher numbers in your data set, it's going to pull the average that direction because you have to add them in there and divide by how many there. So you're looking here-ish, Well, if you look at your averages, are kind of our best estimates here, it looks like it's going down. And so, what period do you think would have the highest mean? It's looking like 1901 to 1930. And you do have to explain why. And you'll need to do some explaining about this, Some things that make an average higher is having more higher, these are higher batting averages, so having more higher numbers makes your average go up. And so you can mention there's a lot of people who have 0.4 or higher on their batting average, whereas here there's very little, and here there are none that are above 0.4. And so there's a lot of things you can mention there. So this is pretty open as to how you answer it, but provide some explanation from the graphs there. And we're going to skip this question for now. We're going to dive into some vocabulary because there's a section that's asking about is this data set discrete or is this data continuous? You have to know what those two words mean. Well, discrete data does not allow for in-between values. Meaning there's typically no fractions, there's no decimals, there's no there's no in-between ones. And if you're looking at a graph, it would be like individual dots as you go through it. There's no in-betweenness connecting it all. Whereas if you're looking at a continuous graph, you can have all the in-between values are there. So an example of some discrete data from real life that you would say things that are discrete would be like number of people in a room. Even if someone's missing limbs and stuff, we still count them as a person because we're not heartless. You can count how many socks people have. That's a thing. Usually something either that's a sock or it's not a sock, and then we kind of don't distinguish. Even if it's got holes in it, you'd claim it's a sock. But as soon as you don't feel like it's something you would put on your feet, then it's no longer a sock. If we have a definition, it's something is or isn't. And there's no in-between values. Whereas continuous data set can have those in-between values. And so that'd be things like temperature, right? Something can be 98.6 degrees. Something can be 34.25 degrees. And so the temperature's got all those in-between values, and that's fine. Something like your weight, you can be 14.9 kilograms. That's not a whole lot, but you can be that weight. It's kind of in between. Distance, you can get down to tiny fractions of an inch. So all the in-between values are there. So this is a lot of the things we do measure in life are continuous, but there are some things that are discrete. There's no in-between values. And then there's two other words you need to be aware of. There's quantitative and qualitative. And this one's a lot easier to distinguish. Quantitative means it's a quantity. It's a number. So the temperature would be a number. Number of cards in a deck. That would be a numerical value. Qualitative data is data that's not numerical. So colors are not numerical. Whether you're male or female and someone's having fun outside of their vehicle. Or other, I guess. That's not a number, and so that's qualitative. How someone's feeling, happy, sad, whatever, that's qualitative. And so We got a few questions here. And this is later in your assignment. You have to determine if these things are qualitative or quantitative. I'd like for you to pause the video and write down what you think the answer is. You can actually circle and draw arrows if you need to, but figure it out. All right, let's start at the top. Letters per word. This one's meant to be a little tricky. The number of letters per word is going to be quantitative because it's a number, right? If you think of a word like word, that has 4 letters. Or if you think of the word letters, that's 7 letters, right? That's a number value. Sleep times, like how long did you sleep, is also going to be quantitative. Whereas how well you slept, how did you sleep last night? Terrible, that would be qualitative. And then which data set is continuous? Well, the number of letters in a word cannot be 4.7. It can't be 13 and a half letters. Either something's got 13 letters or it's got 14 letters. There's no in-betweenness. So this one here is actually going to be the discrete one. Here, letters per word. Word, I know how to spell, D. And then which data set's continuous? That's going to be the sleep times. And that's because you can sleep 4.8 hours. You can sleep for 12 days. You can sleep for 12 and a quarter days. Like you can have all the in-between values. Down to the second, down to the millisecond, down to the microsecond, whatever. All the in-between values are there. And there you go. Good luck on your assignment.